Hypothesis testing, while mathematically sound, is not a perfect process. Just as it is possible for a jury to conclude that the defendant is guilty when in fact the defendant is innocent, so it is possible for a researcher to conclude that the treatment did have an effect when in fact some stray random influence actually caused the outcome of the test. Thus, it is possible that the data will lead you to reject the null hypothesis when in fact the treatment has no effect. If a researcher selects an extreme sample by chance, then the data from the sample may give the appearance of a strong treatment effect, even though there is no real effect. There are two errors a researcher can make. A type 1 error is not a stupid mistake in the sense that a researcher is overlooking something that should be perfectly obvious. In most research situations, the consequences of a type 1 error can be very serious. Because the researcher has rejected the null hypothesis and believes that the treatment has a real effect, it is likely that the researcher will report or even publish the research results. A type 1 error, however, means that this is a false report. Thus, type 1 errors lead to false reports in the scientific literature. Other researchers may try to build theories or develop other experiments based on the false results. A type 1 error occurs when a researcher unknowingly obtains an extreme, non-representative sample. Fortunately, the hypothesis test is structured to minimize the risk that this will occur. To avoid the risk of making a type 1 error, a researcher will select a smaller alpha level, a more stringent one, say 0.01 instead of 0.05. This pushes the z-score boundary to the critical region further out into the tail and reduces the risk of error or chance influencing the outcome from 5% to 1%. Whenever a researcher rejects the null hypothesis, there's a risk of type 1 error. Similarly, when a researcher fails to reject the null hypothesis, there is a risk of a type 2 error. By definition, a type 2 error is the failure to reject a false null hypothesis. In more straightforward English, a type 2 error means that a treatment effect really exists, but the test statistic fails to detect it. A type 2 error occurs when the sample mean is not in the critical region, even though the treatment has had an effect on the sample. Often this happens when the effect of the treatment is relatively small. In this case, the treatment does influence the sample, but the magnitude of the effect is not big enough to move the sample mean into the critical region. Because the sample is not substantially different from the original population, it is not in the critical region, the statistical decision is to fail to reject the null hypothesis and to conclude that there is not enough evidence to say that there is a treatment effect. The probability of a type 2 error is represented by a symbol, the Greek letter beta. In each case, there is a chance that the data are misleading and the decision is wrong. The complete set of decisions and outcomes is shown in Table 8.1, also shown on page 215 in your book. As you have seen, the alpha level for a hypothesis test serves two very important functions. First, alpha helps determine the boundaries for the critical region by defining the concept of very unlikely outcomes. More importantly, alpha determines the probability of a type 1 error. When you select a value for alpha at the beginning of a hypothesis test, your decision influences both of these functions. The primary concern when selecting an alpha level is to minimize the risk of a type 1 error. Thus, alpha levels tend to be very small probability values. By convention, the largest permissible value is alpha equals 0.05. When there is no treatment effect, an alpha level of 0.05 means that there is still a 5% risk or a 1 in 20 probability of rejecting the null hypothesis and committing a type 1 error. Because the consequences of a type 1 error can be relatively serious, many individual researchers and many scientific publications prefer to use a more conservative alpha level, such as 0.01 or 0.001, to reduce the risk that a false report is published and becomes part of the scientific literature. At this point, it may appear that the best strategy for selecting an alpha level is to choose the smallest possible value in order to minimize the risk of a type 1 error. However, there is a different kind of risk that develops as the alpha level is lowered. Specifically, the more one controls for a type 1 error, the more chance there is that you will make a type 2 error. As the alpha level is lowered, the boundaries for the critical region move farther out and become more difficult to reach. Figure 8.5 shows how the boundaries for the critical region move farther out as the alpha level decreases. In general, researchers try to maintain a balance between the risk of a type 1 error and the demands of the hypothesis test. Alpha levels of 0.05, 0.01, and 0.001 are considered reasonably good values because they provide a low risk of error without placing excessive demands on the research results.